Welcome back. We are currently studying nonlinear dynamics in this course on advanced dynamical systems. In the past few lectures, we came across the concept of bifurcation diagrams. What bifurcation diagrams tell us is how the bifurcation in the system works, what are the different values of the parameters under which the system can show stability or lack of stability. We will take up this concept in a little more detail today, and we will see how seemingly very similar looking dynamical equations can behave very differently and how we can analyze the same using bifurcation diagrams. So, let us look into some equations which we have in front of us. The 4 equations which you see here are 4 nonlinear dynamical equations, where the right hand side of these equations are different, but they are very similar. For example, in the first equation you have a x minus a x squared, and in the second equation you have x a minus x squared. Then going to third equation you get a x minus x squared, and then in fourth a x minus x cubed. So, they look very similar, but we will see very soon how they are very different in terms of their dynamical behavior. So, let us look into the first equation. So, the equation is dx by dt is equal to a x minus a x squared. Have we come across this equation before? Well, this equation is our logistic equation for population growth, except that the carrying capacity parameter n has been set to 1 here. So, we know the behavior of this equation very well. So, in order to set up the procedure for following equations 2, 3 and 4, let us first analyze this equation, so that we know the steps very well. So, the first step that we would do is we would set this as f of x. Okay. So, f of x is a x minus a x squared. The bifurcation diagram is the diagram on which you have on the x axis you have the bifurcation parameter, and on the y axis you have the equilibrium solution. So, we need to determine the equilibrium solutions of this, and this can be obtained by setting f of x is equal to 0, which means a x minus a x squared is equal to 0, which means a x 1 minus x is equal to 0, which means I have 2 equilibrium solutions for my case. I have the first equilibrium solution x e is equal to 0, and I have the second equilibrium solution x c is equal to 1. So, what would be the axis for my bifurcation diagram? The axis would be simply a versus x e. The information that would go in this bifurcation diagram would be that x e is equal to 0 and x e is equal to 1. So, let us draw in detail the bifurcation diagram. So, I have the axis as the bifurcation parameter A, the equilibrium parameter, the equilibrium solution x e. So, I have 2 equilibrium solutions, x e is equal to 0, this is the first equilibrium solution, then I have x e is equal to 1, this is the second equilibrium solution. So, let me write here x e is equal to 0 and x e is equal to 1. Now, the question which is in front of me is that on what parts of this diagram is the system stable and where is the system unstable. To do that, I will need to look into the derivative conditions. So, I have dx by dt is equal to a x minus a x squared, which is equal to f of x, from where I can write df by dx is equal to a minus 2 a x, and this df by dx has to be determined at equilibrium solutions. So, therefore, df by dx at x e is equal to 0 is a, and df by dx at x e is equal to 1 is minus a. So, now I need to determine whether df by dx is greater than 0 or less than 0, and accordingly the system would be unstable or stable. Now, therefore, for the first equilibrium solution x is equal to 1, for a greater than 0 you will have unstable part, because df by dx is a, and for a greater than 0 you will have unstable, and a less than 0 you will have the stable part. Similarly, now since I have minus a, for a greater than 0 I will have the stable part of the bifurcation diagram, and for a less than 0 I will have unstable part. So, let me identify these 4 cases on this diagram. I have here this point, and towards the right of this point I have a greater than 0, and left of this point is less than 0. So, for x e is equal to 0 and a greater than 0, I have this part as unstable and this part as stable. Similarly, about this point, now x is equal to 1, for a greater than 0 I have stable, you can see here. So, therefore, this is stable and this is unstable. So, this is the bifurcation diagram which I get for dx by dt is equal to a x minus a x squared, which is the logistic population growth model which we have studied previously. Now, in a similar manner, can we develop the bifurcation diagram for other systems? Let us look into that. So, now my equation is dx by dt is equal to a minus x squared. So, let me write the equation here, dx by dt is equal to a minus x squared, and I will refer this to as f of x. So, how would I determine the equilibrium solutions? I will set f of x is equal to 0, which means a minus x squared is equal to 0, from where I get x equilibrium is equal to plus or minus root a. So, my bifurcation plot will have the curves plus or minus root a. Now, I will need to determine their stabilities. So, let me do one thing, let me write here f of x is equal to a minus x squared, from where I get df by dx is equal to minus 2x, right. So, from here I can make this as d f by dx at plus root a is equal to what? Minus 2 root a. Okay. And since a is under the root, it has to be a quantity which would give me a real quantity, because my bifurcation plot is has a real axis. So, therefore, I can write that this will always be less than 0, which means my system is stable. Okay. And d f by dx for minus root a would be what? 2 root a, which would always be greater than 0, which means I have unstable part. So, how would I use this information to develop the bifurcation plot? So, my equation is dx by dt is equal to a minus x squared, from where I get x equilibrium is equal to plus or minus root a. So, on this curve, on this plane, I will draw the axis as a and x e. X is equal to plus root a would look like this. So, this is plus root a, and x e is equal to minus root a would look like this. This is minus root a. Now, I need to determine whether these two parts are stable or unstable. So, what did I get from the previous analysis? I got df by dx is equal to minus 2 x. So, therefore, df by dx at plus root a is equal to minus 2 root a, which is greater than 0, which is less than 0 always. This is less than 0 always, which means stable, and I can write this here stable. And then df by dx at minus root a was 2 root a, which is always greater than 0, which means unstable, and this means this is unstable. Now, to differentiate the curves on this plane from the axes themselves, let me draw these lines using these red highlighters. This will simply show that your axes themselves are not the equilibrium solutions, because in certain cases your axes themselves may be equilibrium solutions. So, to tell that apart, we have used a red curve for representing the equilibrium solutions. So, now in the previous case, what you saw was that the bifurcation diagram looked like this. In the previous case, equation 1, the bifurcation diagram A versus x e, and equation 2, the bifurcation diagram A versus x e, they looked like this. In the previous case, you had these curves, and now you had these curves, right. We can quickly write stability and lack thereof. Here you have unstable, you have stable, you have stable, you have unstable, 4 parts, and here stable and unstable. And how did the equations look like? Here you have dx by dt is equal to a x minus a x squared, and here you have dx by dt is equal to a minus x squared. You made a small change in the equation, and what you found was that the bifurcation behavior completely changed. We can further appreciate this by looking at other equations. So, let us look at equation number 3. Now, the equation is dx by dt is equal to a x minus x squared. So, let me assign this as f of x. I can determine the equilibrium solution by setting f of x is equal to 0, which means x a minus x is equal to 0, right. So, from here I get x equilibrium is equal to 0 or x equilibrium is equal to a. I get 2 equilibrium solutions as x equilibrium is equal to 0 and x equilibrium is equal to a. Let me draw these curves. So, I have x equilibrium is equal to 0 and x equilibrium is equal to a. These are the 2 equilibrium solutions. Let me draw the axis for the plane. I have a, I have x e. So, what would be the first curve? That would correspond to x equilibrium is equal to 0, and this is what I was referring to, that I have the curve which is the same as your a axis. So, this is my first solution. So, this is x e is equal to 0, and then the second solution equation is x e is equal to a. Okay. Now, x e is your y axis and a is your x axis. So, this is basically the equation y is equal to x. So, x e is equal to a is the equation of the straight line y is equal to x. So, this is going to be your curve, and this is x e is equal to a. Now, let me analyze different parts of these 2 lines and analyze whether the which part is stable and which part is unstable. So, my equation was dx by dt is equal to a x minus x squared. Okay. So, let me check whether this was the equation, a x minus x squared, correct. So, this was the equation. So, then what I will do is I will assign this as f of x, from where I get df by dx is equal to a minus 2 x. Okay. So, df by dx is equal to a minus 2 x, and this has to be determined at x is equal to 0 and x is equal to a. So, therefore, df by dx at x e is equal to 0 is a. Okay. So, like what I did for the case of logistic equation, I can do this analysis that for a greater than 0, I have the unstable part, and a less than 0, I have the stable part. Not very difficult to see. Then I will determine df by dx at x e is equal to a, and this is equal to a minus 2 a, which means minus a. And for this case, for a greater than 0, I will have stable part, and for a less than 0, I will have unstable part. So, now I can determine various parts of my bifurcation diagram and determine whether they are stable or unstable. So, let me see here, I have df by dx is equal to a and a greater than and this was determined at x e is equal to 0, which means this horizontal line, and for a greater than 0, this is unstable. So, this means this is going to be unstable, and for a less than 0, this is going to be stable, right. So, about this point I determined the stability. What about the x is equal to y line or x e is equal to a line? For a greater than 0, I have stable, which means this part, the upper part is stable, and a less than 0 is unstable. So, this part is the unstable part. And what I see is that as I change the value of a in this particular phase, in this particular bifurcation diagram, I go, if I start from stability, I pass through a point beyond which my system becomes unstable, or if I start with a unstable point, I reach a particular point beyond which my system becomes stable. So, you go from stable to unstable, stable to unstable, or unstable to stable, unstable to stable, passing through one specific point, and therefore, the bifurcation diagrams of this nature are called transcritical, and the bifurcation is called transcritical bifurcation. Okay. So, the bifurcation diagram shown here is called transcritical bifurcation. And what would you call that particular point where this point where these two curves meet, where you go from critical, you go from stable to unstable, unstable to stable, and so on? You would call this point as critical point. Okay. And again you would see that you changed the nonlinear equation a little bit, and what happened was that you changed your bifurcation diagram altogether. The features, the curves on the bifurcation diagram changed. Let us look into the final equation. So, the equation now is dx by dt is equal to a x minus x cubed. Now, this is a cubic equation. So, therefore, you may expect 3 equilibrium solutions. Let us see. So, let us assign this as f of x. If I assign this as f of x, then f of x is equal to 0 means a x minus x cube is equal to 0, which means x a minus x squared is equal to 0. So, now if this is the case, then I get my first equilibrium solution as 0, I get my second equilibrium solution as plus root a, and I get my third equilibrium solution as minus root a. Okay. So, before I decide anything about the stability, let us first draw the various portions of the bifurcation plot itself. So, 0 plus root a minus root a. So, and my equation is a x minus x cubed. So, my equation is dx by dt is equal to a x minus x cubed. X e is equal to 0, x e is equal to plus root a, and x e is equal to minus root a are the three equilibrium solutions. So, I will draw the curves, I will draw the first the plane is this, I have a, I have x equilibrium. So, my first solution is x e is equal to 0, this is my first solution, x e is equal to 0. My second solution is x e is equal to plus root a. So, x e is equal to plus root a, and my second solution is x e is equal to minus root a. X e is equal to minus root a. Now, time to identify the stability and or instability of various parts of this plane. So, if I assign this as f of x, then I can write df by dx as a minus 3 x square. So, therefore, df by dx at x equilibrium is equal to 0 is a very similar situation which we encountered before. So, therefore, for a greater than 0, I have unstable part, a less than 0, I have stable part. Fine. Now, df by dx at x equilibrium is equal to plus root a would be what? 3 a minus 3 root a squared is again a. So, this is minus 2 a, this is minus 2 a. So, I can again write this as a greater than 0 stable, a less than 0 unstable. Fine. Finally, df by dx at x e is equal to minus root a is what? A minus 3 times minus root a squared, it is again minus 2 a. So, it would be just a repetition of what we have written above, a greater than 0 stable, a less than 0 unstable. So, time to mark the plane here. First, the equilibrium solution x e is equal to 0. For a greater than 0, I have unstable part. So, this is unstable, a less than 0, I have stable. So, this is stable. Now, for the upper curve df by dx is equal to plus root a, the curve exists only in the first quadrant, there is nothing in the negative a. So, therefore, the only curve which is present here is the stable one. This is stable. You can see from df by dx at x is equal to root a is minus 2 a, and a is always greater than 0 in this, and same is the case for the lower curve. This is also stable, and all these 3 points meet here. And to mathematicians, when they looked at this diagram, it reminded them of one specific tool which is used in farms, and that is called a pitchfork. These lines which are highlighted in red, they look like a pitchfork, okay? And therefore, this bifurcation is called pitchfork bifurcation. Okay. This bifurcation is called a pitchfork bifurcation, and this again has very different characteristics as we saw in this particular case vis-a-vis all the other cases. So, therefore, when you compare equations 1, 2, 3 and 4, what you see is that they look similar, they are not same obviously, and if they are not same, the dynamical behavior may not be expected to be the same obviously, but they are very similar, and small changes in the parameters or the variables or their powers result in drastic changes in the bifurcation behavior of the system. So, we will stop here today, appreciating that bifurcations in nonlinear systems can show very different behaviors depending upon the functional form of the function which you have in the equation. And we have taken a lot of examples of different first order nonlinear systems. Now, I believe it is a good time to go to higher order systems. So, in the next lecture, we will start with higher order nonlinear dynamical systems. Thank you.